I want to talk about secant lines and tangent lines. In particular, I want to talk about their slopes so that we can talk about average rates of change. And when we start talking about tangent lines, we can talk about instantaneous rate of changes. Over here, I have a function graph, and I'm thinking about this function as a y equals f of x. I have 2 points on the graph, a comma f of a and b comma f of b. And here I have the computation for slope. Change in y over change in x. F of b minus f of a over b minus a. And that would give me an average rate of change on the interval AB. In fact, every time you hear the word slope, you can think rate of change. Slope of a secant line is an average rate of change over the interval that the 2 points cover. So from from A to B here. We have developed the idea of limit in this first unit of our course. And so what we can do is rethink what we're calling this. Instead of calling that B, we could imagine that it's A plus a little more. It's A plus H. And that would turn my information to something similar. So one way to think about this is I'm just saying that B is equal to A plus H. B is equal to A plus some other number. And so I could redraw the same function going through the same 2 points. We'll pretend those are actually the same. I know I didn't do that particularly well, but we can use our imaginations. I still would have a secant line. And so all of a sudden, this calculation would look just a little bit different. On the top, I would have f of a plus h minus f of a. And on the bottom, I see the role h is really playing. A plus h minus a is just h. H is literally the distance between these values, a and a plus h. And then I could say, well, what if I just started letting h get smaller instead of being this number? Maybe it was a lot smaller. Well, I'd get a different secant line. And I could imagine just letting h get smaller and smaller and smaller until it looks like my line just touches my graph at that one point, or touches my graph at that one point near it. Maybe the function does something wild and it crosses over it in some other place, and that would be fine. Well, I'm imagining that h is getting smaller. I'm imagining that h is tending towards 0. And this is the language of limits. What I have written here is a formula for the slope of a secant line, just like this. To turn it into the slope of a tangent line, I need to let h go to 0. If I can evaluate this limit, it gives me the slope of a tangent line. So if I was defining slope of a tangent line, I would say it's this expression provided this limit exists. All right, and the slope of a tangent line always tells me an instantaneous rate of change, how fast I'm moving at that specific point. And I ran out of room here, so I'm going to write ROC, instantaneous rate of change. Oh, and that's off the bottom of the screen. I'll just move that down a little bit. There we go. The slope of a tangent line, and that's an instantaneous rate of change. I'm going to post an example next of finding the equation of a tangent line.